fact, thought processes, reasoning, biased way of thinking, and an ordered way of thinking. But logic, at least in the way we're going to use it in this class, is not the same thing as common sense per se. Mathematical logic, which means it's going to have a very clear set of rules. And those rules sometimes connect really well to what we think of in the everyday sense when we mean logic, but they don't always. Sometimes there are surprising things that occur when we follow those rules. Now I'm going to ask you to tell me what you're thinking about proof. When we think about what we typically think of as scientific thinking, we think if you do the same experiment twice, you should get results. If you read a paper, somebody else should be able to go out and do an experiment and get the result. And they found that this isn't happening at the rate you would hope for. If you actually carefully look at scientific papers and you give a result to a different scientist, they do this experiment, lots of times they don't get the same result. And the question is, why is that happening? So what we might think of as proof, as like, I have this ticket that proves I was at a concert. Mathematical proof is a little bit different. Because it's different, it's stronger. Lots of people are surprised, are aware that mathematicians still publish papers, that there's new math being made. 2 people, or 3 or 4 people. So when I was a student, when I was in my first year and part of my second year, I did not. I thought you got to differential equations, and then from there on out, it was just like solve this differential equation for the rest of your life. I didn't know that there are new mathematical ideas that are still being developed. And if you think about it, it's hard to be a mathematician who tells the truth because it sounds arrogant. But you have to think about math compared to other disciplines and where it was. So in math, this is actually a math paper, draft observables in the 4-dimensional phase space of Ashkatar's variables and spherically symmetric loop quantum black holes. I have no idea what most of these words mean because you specialize. Professional mathematicians aren't experts in everything. You have a few things that you're really good at. What I want you to look at, if you would with me, is something that may surprise you if you haven't looked at something like this before, which is people often start looking at these mathematical works and wondering where the math is. Because if you think of math as just symbols and equations, you're not seeing a whole lot. Like here is a variable going to infinity. But we're 2 pages in. What percentage of this work would you say has been verbal and written compared to symbolic and calculation? 99%. It's almost all words. So now we got an equation. Now that we have some context and know what we're talking about. And we're going to start getting some equations, but still, equations are not the majority of any. There's tons of explanation, and it's going to be like that. That was a paper, I just picked at random. We didn't pre-negotiate this. So would someone else give me another word we could look for? Okay, we all might appreciate this then. What if we did jellyfish, man? There we go, jellyfish swarms of elliptic curves. I have no idea what that means either. All right, so here's the paper. Well, they got right to the equation more quickly. But even so, look at the ratio of words to mathematical symbols. I'm not cherry picking anything. I'm just showing you that in math, words are really important. And something that a lot of people don't know about math is as you advance in your studies, words become more and more important. Typically, you're doing a handful of calculations. But what's really important is why you're doing those calculations and how they connect to each other, and you need words for those. So we're going to be doing a lot of writing in this class, and that we provide appropriate evidence and support for what we're trying to show.